A car every 5 seconds sounds impossible, but that is the claim now orbiting Tesla's next manufacturing leap. Not a battery module, not a door panel, a whole vehicle moving through production at a pace closer to a high-speed printer than a traditional auto plant. Here is the catch. Tesla is not building finished cars every 5 seconds today. Even its fastest factories still operate on real-world cycle times, supply chains, inspections, and human bottlenecks. So the real story is not whether a magic machine suddenly spits out cars, it is whether Tesla can redesign the factory itself around the Giga Press, unboxed assembly, and a radically simpler cybercab before one missing piece breaks the entire plan. Tesla's biggest bet is that the car is not the main product, the factory is. For most automakers, manufacturing means taking a complicated vehicle and making the production line efficient enough to handle it. Tesla tries to reverse that order. It asks what the factory should be able to do first, then pushes the car design to fit that process. That is why part count matters so much. Every bracket, weld, bolt, and seal is not just a component. It is a station, a robot movement, a quality check, a delay risk, and a supply chain dependency. Remove the part, and the factory does not have to become slightly faster. It gets to skip an entire step. This is the same kind of shift that changed car making before. Ford did not simply build the Model T faster. He organized the entire factory around flow. Toyota did not simply inspect defects better. It built a system that exposed problems earlier and reduced waste at every stage. Tesla's version is more aggressive. The company wants the product, the machines, and the building to be designed as one system. If a casting can replace dozens of stamped and welded pieces, the line shrinks. If wiring is simpler, assembly becomes easier to automate. If the vehicle has fewer variants, scheduling becomes less chaotic. That raises the real question behind the 5-second car idea. If Tesla can simplify the vehicle enough, can a car factory start to behave less like a traditional auto plant and more like an electronics line, where modules come together quickly, cleanly, and with fewer interruptions? That is the strategy. Not polishing every old step, but deleting as many steps as possible. And the machine that made this philosophy famous is the one Tesla placed at the center of its manufacturing revolution, the Giga Press. The Giga Press is not a normal stamping machine scaled up. It is a giant high-pressure die-casting system that injects molten aluminum into a massive mold, then opens to release a structural section of the vehicle in one piece. Tesla did not invent die-casting, but it pushed the process into territory that traditional automakers had avoided. To do it, Tesla worked with Idra, the Italian casting machine specialist now under LK Technology. Idra supplied the huge presses that made Tesla's single-piece structural castings practical at factory scale. The most famous example is the Model Y rear underbody. In a conventional design, that section can require roughly 70 separate stamped or welded parts. Each part needs tooling, positioning, joining, inspection, and tolerance control. Tesla replaced that cluster with one large aluminum casting. That change removed welds, fixtures, robots, and handling steps from the line. It also reduced the stack-up of small dimensional errors that happen when many pieces are joined together. Instead of building the rear structure piece by piece, the factory receives a large finished section that can move directly into the next stage of assembly. The press itself is enormous because the mold must be clamped shut while molten metal is forced into it under extreme pressure. For the Model Y, Tesla used machines commonly described at around 6,100 tons of clamping force. For the Cybertruck, the scale moved higher, with a 9,000-ton Giga Press used for its much larger castings. Those numbers matter because they show the progression without turning it into mythology. Tesla has proven large structural casting in production, but the industry has not suddenly jumped to complete cars popping out of molds. The biggest confirmed machines in the wider industry are around 16,000 tons, and even those are aimed at very large cast components, not an entire vehicle body in one shot. Still, the direction is clear. If 70 parts can become one, the next question is how many more sections can be combined before physics, materials, cooling, repairability, and cost push back. That is where the fantasy of a car built in seconds begins to collide with the real engineering limits. The rumor now jumps to a far bigger machine, a 50,000-ton Giga Press, sometimes called Giga Press 4.0. In the viral version, this press is already turning complete Tesla bodies into finished structures in a few seconds. That is not confirmed reality. There is no public evidence that Tesla has a deployed 50,000-ton production press building cars in seconds. There is also no confirmed factory line where a complete vehicle structure enters as raw aluminum and exits ready for final assembly after one cycle. The largest verified Tesla casting systems are still tied to specific structural parts, not an entire car body. So why does the 50,000-ton idea keep spreading? Because the logic is tempting. If a 6,100-ton machine can cast a Model Y rear underbody and a 9,000-ton machine can handle a much larger Cybertruck section, a much stronger press suggests a path toward combining even more of the vehicle into fewer pieces. In theory, a giant press could cast multiple large structures in one shot, or produce a single megastructure that replaces whole zones of welded metal. That would remove more robots, more fixtures, more conveyors, more inspection points, and more time between stations. The appeal is not just fewer parts, it is a shorter factory. This is where the car in seconds claim needs precision. Tesla's high-volume manufacturing today is already extremely fast by automotive standards, but it is closer to tens of seconds per unit at peak flow. Not one fully built car every 5 seconds from a single magic machine. A 5-second target has been discussed more as a future ambition linked to very high-volume cybercab production, not as a proven result happening now. A 50,000-ton press would also create new problems. Larger castings need controlled metal flow, fast and even cooling, massive dies, reliable part ejection, and strict quality checks for hidden defects. The bigger the casting, the more expensive a mistake becomes. That makes the mystery important, not fake. A machine on that scale would signal a serious attempt to collapse body production into fewer steps than any normal car factory. But until Tesla or its equipment partners confirm it in operation, the 50,000-ton Giga Press belongs in the category of roadmap, prototype, or thought experiment, not finished factory miracle. The missing half of the speed equation is not the press. It is what happens after the press. Tesla calls the idea unboxed assembly. Instead of building a vehicle as one growing object moving down a long line, the factory builds major sections in parallel. The front structure, rear structure, battery pack, interior seats, doors, and electronics can be worked on separately, then brought together much later in the process. That sounds simple, but it changes the entire factory layout. In a traditional line, workers and robots keep adding parts to the same car body as it travels from station to station. If one step slows down, the cars behind it wait. If a tool, part, or inspection point is not ready, the whole flow can lose time. Unboxed assembly tries to remove that dependency. Each module can have its own shorter work zone, with fewer people walking around a full vehicle shell and fewer parts being carried across the building. The car is not dragged through hundreds of steps before it becomes valuable. More of the work happens at the same time. This is why casting and unboxed assembly fit together. Large castings reduce the number of body pieces. Unboxed assembly reduces the number of times those pieces have to pass through a conventional line. One attacks part count. The other attacks factory motion. Tesla has described this as making vehicles more like consumer electronics. A phone is not assembled by pushing one empty frame through a giant building while every tiny part is added in sequence. Subassemblies are prepared separately, tested, and snapped into a final product at high speed. For cars, that is much harder. The structure must handle crashes, water sealing, wiring, service access, battery integration, paint, and final quality checks. The design has to be planned around the factory from the first sketch, not adapted after the vehicle is already engineered. That leads to the real question behind the next Tesla platform. What kind of vehicle must be designed from scratch to make unboxed assembly actually work? The answer is Cybercab, because it removes the hardest thing to simplify in a normal car, the human driver. Tesla's Cybercab is planned as a small autonomous two-seater with no steering wheel, no pedals, and no mirrors. That is not just a design choice for passengers, it is a manufacturing choice. Every deleted control removes brackets, sensors, wiring, trim pieces, adjustment hardware, validation steps, and installation time. This is why Cybercab may be the cleanest test case for Tesla's next factory system. A conventional vehicle has to support many versions, many driver interfaces, and many comfort layouts. Cybercab can be designed around one job, carry two people autonomously at low cost, with a target price under roughly $30,000. Tesla has suggested that the structural part count could fall dramatically. One comparison often discussed is around 80 major structural components for Cybercab, compared with far more in a conventional vehicle such as Model Y. That difference matters because every component has to be stamped, cast, welded, bonded, moved, checked, and tracked. The exterior may also be designed to reduce one of the slowest and most expensive parts of vehicle production: paint. If Cybercab uses glossy, molded panels or molded-in color finishes, Tesla could shrink the role of a traditional paint shop. That would remove ovens, chemical handling, long cure times, and a major source of factory bottlenecks. Underneath, Cybercab can borrow lessons from structural battery thinking, where the pack is not just energy storage but part of the vehicle's body. It can also benefit from the simpler electrical approach Tesla explored with 48-volt systems, reducing current, cable thickness, and wiring complexity. All of this points toward the same target: fewer parts, fewer stations, fewer hands, and fewer hours. Tesla has described an ambition of producing roughly one Cybercab every 10 seconds. The more aggressive theoretical goal is closer to 5 seconds. That number only makes sense if the car is not merely built faster, but designed so the factory has far less to do. A Cybercab factory only becomes revolutionary if the Cybercab can leave that factory and immediately earn money without a driver. That is the missing variable in the entire manufacturing story. Tesla can cut parts, compress assembly time, and cast larger sections of the vehicle, but the business case depends on unsupervised self-driving, not driver assistance, not a beta system with a human ready to intervene. A robo-taxi needs legal approval and reliable autonomy in real streets, with real pedestrians, cyclists, construction zones, emergency vehicles, bad weather, and unpredictable human behavior. This changes the risk completely. If Tesla builds a normal car too quickly, it can still sell that car to a customer. If Tesla builds cybercabs before the autonomy is approved and trusted, those vehicles can become stranded inventory. They would be cars with no steering wheel, no pedals, and no obvious fallback use. A fast factory would then be producing assets that cannot perform their only job. That is why manufacturing speed cannot be judged in isolation. A cybercab produced every few seconds sounds spectacular, but a robo-taxi network needs utilization. The vehicle must spend most of its life carrying paying passengers, not waiting for software validation, regulatory clearance, or remote support. The profit is not created at the casting machine. It is created when the car safely completes trips at scale with lower operating cost than a human-driven ride-hailing vehicle. There are also trade-offs in the manufacturing strategy itself. Gigacasting can simplify production, but large structural castings may make some crash repairs harder. If a traditional car has a damaged rear section, repair shops may replace smaller welded or bolted components. If a huge casting is damaged in the wrong area, the repair can become more complex, more expensive, or even uneconomical. Insurers care about that. Higher repair costs can feed into higher premiums, which matters for any fleet trying to win on cost per mile. Tesla also does not have the field to itself. Chinese automakers and suppliers have been moving quickly into very large casting machines, fast development cycles, and lower-cost electric vehicle platforms. Companies in China are already using massive presses and pushing aggressive factory integration. So the advantage is not simply owning a bigger machine. Competitors can buy large equipment, copy visible factory ideas, and improve their own processes. The real moat is harder to copy. Tesla needs the vehicle hardware, autonomy software, factory design, battery cost, regulatory approval, service model, and ride-hailing economics to click together at the same time. If one piece is missing, the Giga Press is just an impressive tool. If every piece works, then the factory is not only building cars quickly, it is building a transportation network. The most honest answer is that the Giga Press and unboxed assembly are real breakthroughs, but the 5-second car is still a target, not a present-day fact. Tesla is betting that the biggest advantage will not come from one vehicle, one casting, or one robot. It will come from the machine that builds the car faster than anyone else. Thanks for watching. In the comments, tell me which bottleneck matters more, the factory breakthrough or autonomy, and watch the next video to keep going.